This is the moment you've all been waiting for. We are starting calculus. Okay, if you didn't watch the videos on limits, then you have to go back and do this first. I'd like to start this video by a quote of an article by Stefan Strogatz published in the New York Times. He writes really well, so I would encourage you to pause the video and read. The main ideas for us is the fact that calculus is the mathematics of change. Now we're going to be doing derivatives, and it's all about measuring change. In other words, measuring how fast something is changing. Let's see how it's done. In order to measure how something is changing, calculating rate of change seems like a very natural approach. In this example, we have a quantity called y, which is equal to x squared. Our goal in this example is to figure out how y changes when x changes and x is equal to 2. We don't really know how to do this, so what we're going to do is try to measure the average rate of change when x goes from 2 to 3. Then we'll take a smaller interval when x goes from 2 to 2.5, then an even smaller one. And then we'll try to take one arbitrarily small by making h as small as we'd like. So let's try. We want to measure the average rate of change, which is equal to the change in y divided by the change in x. Here we're using the notation very common in physics to use capital delta to indicate a change. The change in y is the final value of y minus the initial value of y. The change in x, written delta x, is the final value of x minus the initial value of x. That's a 9 minus 4 over 1. So the average rate of change of y on the interval 2, 3 is 5. And we proceed in exactly the same fashion for all the others. We notice that as the intervals get smaller and smaller, the average rates of change on those intervals seem to be getting smaller. And we're wondering if we really make this interval really small by making h approach 0, what rate of change would we get? This is called the instantaneous rate of change. Let's try. So the rate of change will be the change in y divided by the change in x. So that's the final value of y, which is x squared, and x is 2 plus h, minus the initial value of y over the change in x, final value of x, minus initial value of x. Let's expand the top. We get 4 plus 4h plus h squared minus 4, and at the bottom we get h. So the 4's cancel, and we're left with 4h plus h squared on h, and we notice that we can divide the top and the bottom by h, and if we do so we get 4 plus h. But now this lets us know what the instantaneous rate of change is. That's what you get when h approaches 0. And if h approaches 0, then the limit of 4 plus h will just be 4. So we were able to determine the instantaneous rate of change. Let's now try a different approach. Let's say you want to know how y changes when x changes close to some point. What you could do is zoom in, and zoom in again, and zoom in again. In most cases, you will end up getting something which will look like a straight line. When this happens, we say that the function is differentiable. In that case, the straight line we get is going to be called the tangent line, and its slope will be called the derivative of f at this point. Let's see how this enables us to measure change. A good straight line approximation to f of x near 3 is given by this tangent line, right? And indeed, you can see that if you zoom in and zoom in and zoom in, the tangent line will be a very good approximation for the curve around 3. So by eye, we can see that the y-intercept is 1, and here, if we try to calculate the gradient, we're going to be rise over run. We can see that the rise was 1 and the run was 3, so the gradient is going to be 1/3. Therefore, the equation of the line will be y is equal to gradient times x plus y-intercept. The slope of this tangent line is 1/3. We call this number the derivative at x is equal to 3, and we write f dash of 3 is equal to 1/3. The dash means derivative, this 3 here means at 3, and this 1/3 is the value of the slope of the tangent line. Okay, let's try to interpret this. So we want to relate this to change. So assume x changes by a small amount, and for a small change we usually use lowercase delta, whereas for large change we use uppercase delta, which was this triangle. And we want to measure the corresponding change in y. So if we use the straight line instead of the curve, what we see is that that's going to be the change in x, that's going to be the change in y, and if this change occurs along the line, then the gradient is equal to rise over run, but that's exactly the change in y divided by the change in x, and we said that this was 1/3. As a result, the change in y is equal to 1/3 times the change in x. In other words, the change in y is 1/3 of the change in x. If the gradient had been, let's say 5, the change in y would have been 5 times the change in x. The slope of the tangent line does a good job relating the change in x to the change in y, right? Now this method has its limits, it's graphical, so we can't really imagine that each time we want to find the derivative we're actually going to graph the function, estimate the tangent by I, and try to find its equation to determine the slope. We need an idea. We would like to calculate the slope of the tangent line at A. But the problem is, we know only one point on this line, and usually every time we calculate the slope we need 2 points. So maybe what we could do is look at another point on this line. So I'm looking at the point with x coordinate equal to a plus h. Let's draw the line AM. For this line it's fairly easy to calculate the slope. I know what you're going to say. You're going to say, but this is the slope of the wrong line. What's easy to calculate is the slope of the green one, and the one we want is the slope of the red one. But say we start making h smaller and smaller and smaller. The green line gets closer and closer to the red line, which means that the slope of the green line is becoming closer and closer to the slope of the red line, which is what we're trying to find. And that gives us an idea. What we could actually do is, so I'm just showing you it works also from the other side, is calculate the slope of the green line and then take its limit as h approaches 0. This is our strategy to calculate the slope of the tangent line, in other words, the derivative. Let's use this idea to find a formula for the slope of the tangent line. So, okay, we can't get the slope of the tangent line directly, so we start by getting the slope of this green sequent, and then we take the limit as h approaches 0. We're interested in the slope, that's rise over run, change in y over change in x, so your rise is f of x plus h minus f of x. Your run, which can be seen here or there, is x plus h minus x, so that's your h. And then, as we said, just make this point get closer and closer and closer to that one. So that means let h approach 0, and your green line will get closer and closer and closer to the red one. So if what you're interested in is the slope of the tangent line, just take the limit of the slope of the green line as h approaches 0. Note that this is the average rate of change of y equal to f of x in the interval x plus h. And then we take the limit, making the interval smaller and smaller and smaller. So that really is the instantaneous rate of change. So our two approaches end up giving the same definition for the derivative. Now what we just did here for this fixed value of x can be done for any x. So for any x, we can find the slope of the tangent line if such a thing exists, and that defines a new function. So what we will remember from all of this is that f dash of x is defined to be the slope of the tangent to the graph of f at x if the slope exists, and that it can be obtained by calculating an average rate of change between x and x plus h, and then taking its limit as h approaches 0. And this indeed will be the way to recognize whether a function is differentiable at a point. If this limit exists, this limit here, we say that the function is differentiable. Maybe at this point you're not exactly sure how it's possible for the tangent line not to exist, what a non-differentiable function would look like. Well, it's a function for which when you zoom in and zoom in and zoom in, you don't get a straight line. For example, in that case, if you zoom on this sharp corner, well, it will always look like a sharp corner. There's no real way to fit a tangent there, right? And same thing here. You don't really get a straight line. You get this gap. So in short, by looking at the graph, you will realize that a function is not differentiable because if you zoom in and zoom in, you don't really get a straight line. And if you don't have the graph and you just use the previous formula, you will realize that your limit doesn't exist. In this example, we're asked to find f dash of x, the derivative of x, using the definition of the derivative. Sometimes you will get the exact same question telling you find the derivative from first principle. So far anyway, the only thing we have is the definition, but that means as opposed to using formula. So the definition we are allowed to use is this one. We're going to do this in two steps. First, we're going to calculate this average rate of change, and then we'll apply the limit as h approaches 0. Let's start. So the change in y divided by the change in x is always the final value of y, f of x plus h, minus f of x over h. Really, I'm just copying this part. Now let's apply it to our function. So, if you look at the definition of the function right here, it really means, and if you read it this way it will help, f of the input is equal to the square of the input minus 4 times the input minus 8. In this, the input is x plus h. So let's do just that. We need to find the square of the input, that's x plus h squared, minus 4 times the input, minus 8. And we took care of this, right? It's exactly the same as that. Now we need to subtract f of x. So we subtract f of x, we have it here, so we just copy this down. And we're getting x squared minus 4x minus 8. At the bottom we get h, that's easy. We know that our final goal is to find the limit of this quantity as h approaches 0. And it is, and will always be, an indeterminate form of type 0 over 0. Always, I mean whenever you try to find derivatives using this. I'm not saying we should give up because it's not going to work. It will. So the first thing we're going to do is try to simplify this expression. And we're going to do this by expanding. So for the first term, we will use the perfect square formula. So that gives us an x squared plus 2xh plus h squared. Then we can distribute this negative 4, and we're going to get minus 4x minus 4h, and then we get the minus 8, and then we can distribute this negative sign again, and that's going to give us minus x squared plus 4x plus 8. Sorry, desperately trying to go back to blue. That's done. And we can see that a lot of terms cancel. Plus x squared minus x squared. Minus 4x plus 4h. Minus 8 plus h. So what is left is this term and those two. So we get 2xh plus h squared minus 4h divided by h. And we can see that at the top there is a common factor of h. So we can divide the top and the bottom by h, and we're left with 2x minus 4 plus h. Remember, the goal was to find the derivative, which is obtained by taking the limit as h approaches 0 of this average rate of change. So what we need to find is the limit as h approaches 0 of the rate of change, which we just calculated. So that's really the limit as h approaches 0 of 2x minus 4 plus h. The first two terms are fixed, they don't depend on h, and this one goes to 0. So the limit we get is 2x minus 4. For those of you who already know the formula, that shouldn't come as a surprise. So we know that the result of this calculation is what is called the derivative. So we manage to get this formula. And actually all the formulas we know, and we'll talk about later on, are obtained using this definition. Thank you for watching this video.